on the variational formulation that we have started in our previous lecture. So, today what we are going to look at is the transverse vibrations of a hanging chain. So, this is a chain, as you can see, this is an inextensible continuum. So, we are going to look at the equation of motion of such a chain. So, let us consider this chain hanging in a uniform gravitational field . So, we assume that this chain is made of a material of density rho, has a constant area of cross section A, has a length L. Now, this is an inextensible chain. So, though it does not in a way resemble a string in that sense, which is an elastic continuum, one dimensional elastic continuum, this is inextensible. Yet, as we will see very soon, the equation of motion, at least up to the linear order, is similar to that of a string. So, we are going to write down the energy expressions. So, the kinetic energy. So, at any location x, our field variable is w x comma t. So, the kinetic energy of an infinitesimal element can be written as half rho a dx is the mass of the infinitesimal element, and velocity square. So, if I integrate this over the length of the string, then what I have, this is the kinetic energy. Now, the potential energy. Now, the potential energy of this chain. Now, why this chain restores back to its vertical position? It is because as it deflects or as it is disturbed, the potential energy of the chain changes. So, it increases. Now, to calculate that, let us look at a small element of this chain. So, this is the undeformed configuration of the chain, and this is the deflected configuration. So, this infinitesimal element had a length dx. Now, since this chain is inextensible as we have assumed, so the length of this infinitesimal element in the undeflected or in the equilibrium configuration is same as in the deflected configuration. So, this is also dx, but now this is deflected. So, I will represent it as a vector whose length or whose magnitude is dx, and these vectors I will represent as this way, and this vector at x plus dx is given by this vector. So, if you write out this vector equation, so we can represent this ds vector in terms of the deflection of the chain. Now, if you take the magnitude of the vectors on both sides, then as I mentioned that the magnitude of this is still dx because the chain is inextensible. So, what I will do is I will take the magnitude square, let us say, and if you simplify the right hand side, we have this expression from which we can write now. Here I have made this approximation. So, in this step, while coming from this step to this step, I have made this approximation that del u del x is much smaller than 1. So, the expansion of this I have in this expansion I have dropped del u del x whole square. So, this implies or so, I have represented the axial deflection or axial motion of the chain. Now, this is very different from that in strings. So, in strings we had neglected the axial motion, but in a hanging chain we must consider this axial motion, because that is the reason why the potential energy of the chain is changing as the chain deflects from its equilibrium position. Now, once we have this expression of the axial deflection, we can write down the potential energy of the chain. So, rho E into A is mass per unit length, dx that gives the mass of a little element, infinitesimal element of the chain, into the acceleration due to gravity into u. So, that would be the potential energy, and if you integrate over the length of the chain, that will give you the net potential energy, assuming that the potential energy is 0 in its equilibrium configuration. Now, what I can do is I can integrate this expression by parts. I can write this as taking u as the first function and rho a g as a second function, so the first function integral of the second function minus integral of derivative of the first function, the integral of the second function. Now, this simplifies to, so this boundary term can be written as u evaluated at L. So, that would mean this integral with x replaced by L. And one minus from here, when I replace del u del x here, and so this finally simplifies to So, we have the kinetic and the potential energy expressions of the chain. So, let me write them again. So, if you look at these expressions, now this kinetic energy expression, this resembles the kinetic energy of the of a normal elastic string, and this potential energy expression also resembles that of a string, except for this term. Now, in a normal elastic string, this here this term is the tension, which is constant, but in the case of a hanging string or hanging chain, as we know, the tension varies with the location. So, our Lagrangian now may be expressed like this, and from Hamilton's principle, which says the variation of the action is 0, we can write now here once again, as we had done before, we will integrate by parts this term with respect to time and this term with respect to space to obtain So, this is what we obtained finally. Now, here as we had stated before, since we know the configuration of the chain at the time instants t 1 and t 2. So, there cannot be any variation of the configuration. So, this at both times t 1 and t 2, this variation must vanish. Now, here is a term which is evaluated only at the boundaries, and here it is evaluated or it is over the full domain, it is integrated over the complete domain 0 to L. Now, I can always hold the boundary variation fixed and change the inner portion arbitrarily. So, therefore, if this sum has to vanish, they must vanish separately. So, for arbitrary variation, therefore, if this integral has to vanish, then we can write this must be 0, which is our equation of motion of the hanging chain. Now, these boundary terms must also vanish. So, this will give us the boundary conditions. So, let us have a look at the boundary conditions. Now, at x equal to 0, at x equal to 0. So, at this boundary, either this must be equal to 0 or now, in our case, if you consider that the chain is fixed at the top end, then this is the boundary condition. If it is free, then this is going to be the boundary condition. So, these are the possible boundary conditions at x equal to 0, and we can have so, here as you can see that at x equal to L, this term vanishes. Now, this remember was the tension in the string, and tension at the free end of a hanging chain is definitely 0. So, if you this of course, there is a product now. Here in this case of a chain with a free end, this vanishes. Now, in order to have 0 contribution from the boundary at x equal to L, therefore, you must have this variation to be finite, because this part of the boundary term is 0 at x equal to L. So, therefore, we usually write we say that the deflection of the string of the chain at the free end must be finite, and the implications of this boundary condition will be seen when we discuss the solution procedure for the string, the hanging chain. Next, we are going to slightly generalize the procedure. So, we have been looking at action integrals in which the Lagrangian is a function of the velocity, the slope. It may be also a function of the field variable w itself, and it may be a function of time. So, let us slightly generalize what we have been doing for a Lagrangian which has this form, which is a function of the velocity, the spatial derivative of the field variable itself, and maybe time. So, if you say that the variation is 0, that would imply so delta L may be written as in this form. Now, I will integrate by parts the first term in the integrand, first two terms, the first term with respect to time and the second term with respect to space, and of course, this must be 0. So, that implies so here we have minus of derivative with respect to time minus derivative with respect to x and delta W comes out common, and that must be 0. Now, as you know that at these two time instants, I definitely know the configuration of the system, which means I completely know my field variable. So, there cannot be any variation on the field variable at these two time instants. So, if the rest of the terms must vanish for arbitrary variation delta W, you see this term which is evaluated at the boundaries, and this is dependent on the total domain. Now, I can fix the variation at the boundary and change the variation over the domain. So, these two terms must independently vanish for this sum to vanish. So, for arbitrary variation, if this integral is to vanish, then it must be true and this is our equation of motion. And what we have from this term, we have the boundary conditions. So, the boundary conditions, the possible boundary conditions could be so del L del W x at x equal to 0 is 0, or W itself at 0 must be 0, and del L del W comma x at x equal to L must be 0, or W at L must vanish. So, these are the possible boundary conditions for the problem. Now, it so happens that boundary conditions of this type, they are the geometric boundary conditions. While these boundary conditions are the natural boundary conditions of the problem. So, let us look at some applications of this generalized formulation for vibration of bars. So, we consider first axial vibrations of a bar. So, the field variable is u x comma t. So, first we write down the kinetic energy. So, if rho is the density, A is the cross section, then this is the mass of an infinitesimal element into the velocity square, and this integrated over 0 to L will give you the kinetic energy of the bar. Now, the potential energy of the bar may be written from elasticity theory as half times the stress times the strain, and this is per unit volume. So, I must integrate this over the volume. So, if A is the area of cross section, A dx is this little volume element, and this integrated from 0 to L will give us the total potential energy of the bar. Now, strain, as we have derived before, is del u del x, and sigma is so. Therefore, this is the expression of the potential energy of the bar. Now, what we have been describing as the Lagrangian, or what is more appropriately called the Lagrangian density, is given by now, as derived, the equation of motion will be obtained from this equation. Now, as you can see that there is no explicit dependence of this Lagrangian density on u. So, this term here is 0. So, what we have is we have only these two terms. So, del L del u comma t is and del L del u comma x So, therefore, the equation of motion is obtained in this form, which we have derived before as well. And the boundary conditions are obtained, the possible boundary conditions would be so. In this case, of course, the boundary is fixed at x equal to 0. So, this is our boundary condition at x equal to 0, and at x equal to L, this is the boundary condition at x equal to L. There is another possibility which does not apply here. So, if the bar is fixed, if the bar is fixed at the other end as well, then we have this boundary condition, but that does not apply here. So, in our case, for this bar, a fixed free bar, these are the boundary conditions of the problem. Now, let us discuss this for torsional vibration of a circular bar as well. So, if phi is the field variable, then I can write the kinetic energy in this form. Now, to write the potential energy of this bar, so again from theory of elasticity, now as we know that the stress, the shear stress is varying over the cross section. So, I must first integrate over the cross section and then finally over the length. So, this is energy per unit volume, and that I integrate over the total volume to obtain the total potential energy. And we know that the shear strain is given by R times del phi del x, and shear stress is G times the shear strain. So, if you substitute these two expressions in here, this will simplify to g times I p. So, this of course comes with a square. So, that is the potential energy expression for this bar. So, our Lagrangian density is given by this expression. Now, once again we apply our equation of motion. So, which reads once again we find that this Lagrangian density is independent of phi. So, this term, the third term, is 0. So, once I have evaluated these terms, I can now write down the equation of motion. In this form, and the boundary conditions are obtained as at x equal to 0, since this bar is fixed to the wall. So, at x equal to 0, there is no twist in the bar, and at x equal to L, this is a free end. So, phi is not fixed. So, therefore, so this term must be 0, which implies so these are our boundary conditions for the problem. So, this is a natural boundary, this is a geometric boundary condition, and this is a natural boundary condition. So, what we have looked at in this lecture, we started with the vibrations of the dynamics of a hanging chain. We derived the equation of motion and the boundary conditions. Then we generalized the variational approach to finding the equation of motion and the boundary conditions, and we have derived a general form of the equation of motion and the boundary conditions, and we have applied it to two examples. So, we will carry forward this and see applications in other examples in the subsequent lectures. That is the end of this lecture.